So I want to begin by trying to build some intuition for how one might be able to do staging from cross-sectional data. And we'll return to this question of combined staging and subtyping only much later. So imagine that we had data that lived in one dimension. Here, each data point is an individual. We observe their data at just one point in time. And suppose we knew exactly which biomarker to look at. Right? So I gave you an example of that here when you might look at some antibody expression level. And that might be what I'll call biomarker A. And so if you knew exactly what biomarker to look at, you might just put each person along this line. And you might conjecture that maybe on one side of the line, this is the early disease. And on the other side of the line, maybe that's the late disease. Why might that be a reasonable conjecture? What would be an alternative conjecture? Why don't you talk to your neighbors and see if you guys can come up with some alternative conjectures? Let's go. All right, that's enough. So hopefully a simple question, so I won't give you too much time. All right, so what would be another conjecture? So again, our goal is we have one observation per individual. Each individual is in some unknown stage of the disease. We'd like to be able to sort individuals into early and late stages of the disease. I gave you one conjecture of how to do that sorting. What would be another reasonable conjecture? Raise your hand. Yep.
Just that they have different types of the same disease, and that it could just one of the subtypes might be similar to the other.
Yeah. So you're going back to the example I gave here, where you could conflate these things. I want to stick with a simple story. Let's suppose there's only one subtype of the disease. What would be another way to sort the patients given this data, where the data is, these points that you see here? Yeah.
Early disease in the middle range, and then as you go upwards on both sides.
Okay, so maybe early disease is right over here, and when things get bad, this biomarker starts to become abnormal, and abnormality for whatever reason might be sort of to the right or to the left. No, I think that is a conjecture one could have. I would argue that that's perhaps not a very natural conjecture given what we know about common biomarkers that are measured from the human body and the way that they respond to disease progression. Unless you're in the situation of having multiple disease subtypes where, for example, going to the right might correspond to one disease subtype and going to the left might correspond to another disease subtype. What would be another conjecture? You guys are missing the easy one. Yeah, in the back.
Well, there might just be one where the high values are early disease stage and low values are the later ones.
Exactly, thank you. So this might be early disease, and that might be late disease.
It says vice versa on the slide.
Oh, does it really?
Yeah.
Oh, shoot.
Well, still, it's like brackets.
Right, okay, thank you. Next time I'll take out that or vice versa. That's why you guys aren't saying that. Okay. Okay, so this was good. At least now I think we're all on the same page, and we have some idea of what are some of the assumptions that one might need to make in order to actually do anything here. Like, for example, we are making we'll probably have to make some assumption about continuity, that there might be some gradual progression of the biomarker of relevance from early to late, and it might be getting larger, it might be getting smaller. If it's indeed the scenario that we talked about earlier, where we said like early disease might be here and late disease might be going to either side, in that case, I think one could easily argue that with just the information we have here, disease progression, disease stage is unidentifiable, right? Because you wouldn't know where should that transition point be? Is it here, 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 here? In fact, the same problem arises here. Like, you don't know, is it early disease? Is it going this way or is it going that way? What would be one way to try to disentangle this, just to try to get us all on the same page? Right? So suppose it was only going this direction or going that direction. How can we figure out which is which? Yep.
Maybe we had data on, well, we had other data about like how much time they have left. And you could correlate that.
Yeah, no, that's great. So maybe we have data on let's say, death information, or even just age. And if we started from a very, very rough assumption that disease stage, let's say, grows monotonically with age, then, and if you made an additional assumption that the disease stages are, that the people who are coming in are uniformly drawn from across disease stages, with those two assumptions alone, then you could, for example, look at the average age of individuals over here and the average age of individuals over here, and you'd say the one with the larger average age is the late disease one. Or you could look at time to death. If you had, for each data point, you also knew sort of how long until the individual died. You could look at sort of average time to death for these individuals versus those individuals and try to tease it apart in that way. Right? That's what you meant. OK, so I'm just trying to give you some intuition for how this might be possible. What about if your data looked like this? So now you have two biomarkers. So we've only gone up by one dimension only. And we want to figure out where's early, where's late. Already it starts to become more challenging, right? So the intuition that I want you to have is that we're going to have to make some assumptions about disease progression, such as the ones we were just discussing. And we also have to get lucky in some way. So for example, one way of getting lucky would be to have a real lot of data. So if you had a ton of data, and you made an additional assumption that your data lives on some low-dimensional manifold, where on one side of the manifold is early disease and the other side of the manifold is late disease, then you might be able to discover that manifold from this data, and you might conjecture that the manifold is something like that, sort of that trajectory that I'm outlining there with my hand. But for you to be able to do that, of course, you need to have enough data. Right? So it's going to be now a trade-off between just having cross-sectional data might be OK, so long as you have a real lot of that data, so you can sort of fill in the spaces and really identify that manifold. A different approach might be, well, maybe you don't have just purely cross-sectional data. Maybe you have 2 or maybe 3 samples from each patient. And then you can color code this. So you might say, OK, green is patient 1. Or patient A, we'll call it. And this is the first time point from patient A, second time point from patient A, third and fourth time points from patient A. Red is patient B, and you have 2 time points from patient B. And blue here is patient C, and you have 1, 2, 3 time points from patient C. OK? Now, again, it's not very dense data. We can't really draw curves out. But now we can start to get a sense of the ordering. And again, now we could, even though we're not in the dense setting like we're here we'd still nonetheless be able to figure out that probably the manifold looks a little bit like this, right? And so, again, I'm just trying to build intuition around when disease progression modeling for cross-sectional data might be possible. But this is a wide open field. And so today I'll be telling you about a few algorithms that try to build on some of these intuitions for doing disease progression modeling. But they will break down very, very easily. They'll break down when these assumptions I gave you don't hold. They'll break down when your data is high dimensional. They'll break down when your data looks like this, where you don't just have a single subtype, but perhaps multiple subtypes. And so this is really a very active area of research. And it's an area that I think we could make a lot of progress on in the field in the next several years. So I'll begin with one case study coming from my own work, where we developed an algorithm for learning from cross-sectional data. And we evaluated it in the context of chronic obstructive pulmonary disorder, or COPD. COPD is a condition of the lungs, typically caused by air pollution or smoking. And it has a reasonably good staging mechanism. One uses what's called a spirometry device in order to measure the lung function of the individual at any one point in time. So for example, you take the spirometry device, you stick it in your mouth, and you breathe in, and then you exhale. And one measures how long it takes in order to exhale all of your air. And that is going to be a measure of how good your lungs are. And so then one can take that measure of your lung function and one can stage how severe the person's COPD is. And that goes by what's called the GOLD criteria. So for example, in stage 1 of COPD, common treatments involve just vaccinations, using a short-acting bronchodilator only when needed. When the disease stage gets much more severe, like stage 4, then often treatment is recommended to be inhaled glucocorticosteroids if there are repeated exacerbations of the disease, long-term oxygen if respiratory failure occurs, and so on. And so this is a disease that's reasonably well understood because there exists a good staging mechanism. And I would argue that when we want to understand how to do disease staging in a data-driven fashion, we should first start by working with either synthetic data, or we should start with working with a disease where we have some idea of what the actual true disease staging is. And that way we could look to see what our algorithms would recover in those scenarios, and does it align with what we would expect, either from the way the data was generated or from the existing medical literature. And that's why we chose COPD, because it's well understood, and there's a wealth of literature on it, and because we have data on it which is much messier than the type of data that went into the original studies. And we could ask, could we come to the same conclusions as those original studies? So in this work, we're going to use data from the electronic medical record. We're only going to look at a subset of the EMR, in particular at diagnosis codes that are recorded for patient at any point in time. And we're going to assume that we do not have access to spirometry data at all. So we don't have any obvious way of staging the patient's disease. The general approach is going to be to build a generative model for disease progression. At a very high level, this is a Markov model. It's a model that specifies the distribution of the patient's data, which is shown here in the bottom, as it evolves over time, according to a number of hidden variables that are shown in the top, these S variables that denote disease stages, and these X variables that denote comorbidities that the patient might have at that point in time. These X and S variables are always assumed to be unobserved. So if you were to clump them together into one variable, this would look exactly like a hidden Markov model. And moreover, we're not going to assume that we have a lot of longitudinal data for a patient. In particular, COPD evolves over 10 to 20 years, and the data that we'll be learning from here has data only over 1 to 3 year time range. The challenge will be, can we take data in this 1 to 3 year time range and somehow stitch it together across large numbers of patients to get a picture of what the 20-year progression of the disease might look like? The way that we're going to do that is by learning the parameters of this probabilistic model. And then from the parameters, we're going to either infer the patient's actual disease stage and thus sort them, or actually simulate data from this model to see what a 20-year trajectory might look like. Is the goal clear? All right, so now what I'm going to do is I'm going to step into this model piece by piece to tell you what each of these components are. And I'll start out with the very topmost piece, shown here by the red box. So this is the model of the patient's disease progression at any one point in time. So this variable S1, for example, might denote the patient's disease stage on March 2011. S2 might denote the patient's disease stage April 2011. S capital T might denote the patient's disease stage June 2012. So we're going to have one random variable for each observation of the patient's data that we have. And notice that the observations of the patient's data might be at very irregular time intervals. And that's going to be OK with this approach. Okay, so notice that there's a sort of 1 month gap between S1 and S2, but a 4 month gap between ST minus 1 and ST. Okay, so we're going to model the patient's disease stage at the point in time when we have an observation for the patient. S denotes a discrete disease stage in this model. So S might be a value from 1 up to 4, maybe 1 up to 10, where 1 is denoting a early disease stage, and 4 or 10 might denote a much later disease stage. If we have a sequence of observations for a patient, for example, we might have an observation on March and then in April, we're going to denote the disease stage by S1 and S2. What this model is going to talk about is the probability distribution of transitioning from whatever the disease stage at S1 is to whatever the disease stage at S2. Now, because the time intervals between stages are not homogeneous, we have to have a transition distribution that takes into consideration that time gap. And to do that, we use what's known as a continuous time Markov process. Formally, we say that the transition distribution, so the probability of transitioning from stage I at time t minus 1 to stage j at time t, given as input the difference in time intervals, the difference in time points, delta. So delta is the number of months between the two observations. So this conditional distribution is going to be given by the matrix exponential of this time interval times a matrix Q. And then here, the matrix Q gives us the parameters that we want to learn. So let me contrast this to things that you might already be used to. In a typical hidden Markov model, you might have ST goes to ST, or ST minus 1 goes to ST. And you might imagine just parameterizing ST given ST minus 1 just by a lookup table. So for example, if the number of states for each random variable is 3, then you would have a 3 by 3 table, where for each state ST minus 1, you have some probability of transitioning to the corresponding state ST. So this might be something like 0.9, 0.9, 0.9, where notice I'm having a very large value along the diagonal because it's if let's say a very small period of, so a priori we might believe that patients stay in the same disease. And then one might imagine that the probability of transitioning from state 1 at time t minus 1 to state 2 at time t might be something like 0.09, and the probability of skipping state 2 going directly to state 3 from state 1 might be something much smaller, like 0.01. Okay? And we might say something like that the probability, we might imagine that the probability of going in a backwards direction, going from stage 2 at time t minus 1 to, let's say, stage 1 at time t, that might be 0. Right? So you might imagine that actually this is the model. And what that's saying is something like you never go in the backwards direction, and you're more likely to transition to the state immediately adjacent to the current stage, and very unlikely to sort of skip a stage. So this would be an example of how you would parameterize the transition distribution in a typical discrete time Markov model. And the story here is going to be different specifically because we don't know the time intervals. So intuitively, if a lot of time has passed between the two observations, then we want to allow for an accelerated process. We want to allow for the fact that you might want to skip many different stages to go to your next time step, to go to the stage of the next time step, because so much time has passed. And that intuitively is what this scaling of this matrix Q by delta corresponds to. So the number of parameters in this parameterization is actually identical to the number of parameters in this parameterization, right? So you have a matrix Q, which is given to you in essence by the number of states squared. Really the number of states, there's an additional redundancy there because it has to sum up to 1, but that's irrelevant. And so the same story here, but we're going to now parameterize the process by, in some sense, the infinitesimally small time probability of transitioning. So if you were to take sort of the derivative of this transition distribution as the time interval shrinks, and then you were to integrate over the time interval that was observed, the probability of transitioning from any state to any other state with that infinitesimally small probability of transitioning, what you get out is exactly this form. And I'll leave, you can, this paper is in the optional readings for today's lecture, and you can read through it to get more intuition about the continuous time Markov process. Any questions so far? Yep.
So those Q is the same for all patients? Or?
Yes. And in this model, Q is assumed to be the same for all patients. You might imagine if there were disease subtypes, which there aren't in this approach, that Q might be different for each subtype. For example, you might transition between stages much more quickly for some subtypes than for others. Other questions? Yep.
So Q you said it had like it's just like a discrete number. Beforehand you kind of like specify how many stages you pick the disease has.
Correct. Yes. So you pre-specify the number of stages that you want to model, and there are many ways to try to choose that parameter. For example, you could look at held out likelihood under this model, which is learned with a different number of stages. You could use typical model selection techniques from machine learning also as another approach, where you try to penalize complexity in some way. Or what we found here, because of some of the other things that I'm about to tell you, it doesn't actually matter that much. So similarly to when one does hierarchical clustering or even k-means clustering, or even learning a probabilistic topic model, if you use very small number of topics or number of clusters, you tend to learn sort of very coarse-grained topics or clusters. If you use if you use a much larger number of topics, you tend to learn much more fine-grained topics. Same story is going to happen here. If you use a small number of disease stages, you're going to learn very coarse-grained notions of disease stages. If you use more disease stages, you're going to learn a fine-grained notion, but the overall sorting of the patients is going to end up being very similar. But to make that statement, we're going to need to make some additional assumptions, which I'm going to show you in a few minutes. Any other questions? These are great questions. Yep.
So do we know the staging of the disease beforehand?
No, and that's critical here. So I'm assuming that these variables, these S's, are all hidden variables here. And the way that we're going to learn this model is by maximum likelihood estimation, where we marginalize over the hidden variables, just like you would do in any EM type algorithm. Any other questions? All right, so what I've just shown you is the topmost part of the model. Now I'm going to talk about a horizontal slice. So I'm going to talk about one of these time points. So if you were to look at the translation, the rotation of one of those time points, what you would get out is this model. These x's are also hidden variables, and we have pre-specified them to characterize different axes by which we want to understand the patient's disease progression. So in Thursday's lecture, we characterized patient's disease subtype by just a single number. And similarly, in this example, is just by a single number. But we might want to understand what's really unique about each subtype. So for example, what's really unique about each disease stage? So for example, how is the patient's endocrine function in that disease stage? How is the patient's psychiatric status in that disease stage? Has the patient developed lung cancer yet at that disease stage? And so on. And so we're going to ask that we want to be able to read out from this model according to these axes. And this will become very clear at the end of this section, where I showed you a simulation of what 20 years looks like for COPD according to these quantities. When does the patient typically develop diabetes? When does the patient typically become depressed? When does the patient typically develop lung cancer, and so on? So these are the quantities in which we want to be able to really talk about what happens to a patient at any one disease stage. But the challenge is we never actually observe these quantities in the data that we have. Rather, all we observe are things like laboratory test results or diagnosis codes or procedures that have been performed and so on, which I'm going to call the clinical findings in the bottom. And as we've been discussing throughout this course, one could think about things as diagnosis codes as giving you information about the disease status of the patient, but they're not one and the same as the diagnosis, because there's so much noise and bias that goes into the assigning of diagnosis codes for patients. And so the way that we're going to model the raw data as a function of these hidden variables that we want to characterize is using what's known as a noisy OR network. So we're going to suppose that there is some generative distribution where the observations you see, for example, diagnosis codes, are likely to be observed as a function of whether the patient has these phenotypes or comorbidities with some probability. And that probability is going to be specified by these edge weights. So for example, a diagnosis code for diabetes is very likely to be observed in the patient data if the patient truly has diabetes. But of course, it may not be recorded in the data for every single visit the patient has to a clinician. There might be some visits to clinicians that have nothing to do with their patient's endocrine function, and diabetes as a diagnosis code might not be recorded for that visit. So it's going to be a noisy process, and that noise rate is going to be captured by that edge. So part of the learning algorithm is going to be to learn the transition distributions. So for example, that Q matrix I showed you in the earlier slide. But the other role of the learning algorithm is to learn all of the parameters of this noisy OR distribution, namely these edge weights. So that's going to be discovered as part of the learning algorithm. And a key question that you have to ask me is how, if I know I want to read out from the model according to these axes, but these axes are I'm never assuming that they're explicitly observed in the data, how do I ground the learning algorithm to give meaning to these hidden variables? Because otherwise, if we left them otherwise unconstrained, and you did maximum likelihood estimation, just like in any factor analysis type model, you might discover some factors here, but they might not be the factors you care about. And if the learning problem was not identifiable, as is often the case in unsupervised learning, then you might not discover what you're interested in. So to ground the hidden variables, we used a technique that you already saw in an earlier lecture from lecture 8 called anchors. So a domain expert is going to specify for each one of the comorbidities one or more anchors, which are observations which we are going to conjecture could only have arisen from the corresponding hidden variable. So notice here that this diagnosis code, which is for type 2 diabetes, has only an edge from x1. That is an assumption that we're making in the learning algorithm. We are actually explicitly zeroing out all of the other edges from all of the other comorbidities to 0.1. We're not going to pre-specify what this edge weight is. We're going to allow for the fact that this might be noisy. It's not always observed even if the patient has diabetes. But we're going to say this could not be explained by any of the other comorbidities. And so for each one of the comorbidities or phenotypes that we want to model, we're going to specify some small number of anchors, which correspond to a type of sparsity assumption on that graph. And these are the anchors that we chose. For asthma, we chose a diagnosis code corresponding to asthma. For lung cancer, we chose several diagnosis codes corresponding to lung cancer. For obesity, we chose a diagnosis code corresponding to morbid obesity, and so on. Right? And so these are ways that we're going to give meaning to the hidden variables. But as you'll see in just a few minutes, it is not going to pre-specify too much of the model. The model is still going to learn a whole bunch of other interesting things. By the way, the way that we actually came up with this set was by an iterative process. We specified some of the hidden variables to have anchors, but we also left some of them to be unanchored, meaning free variables. We did our learning algorithm, and just like you would do in a topic model, we discovered that there were some phenotypes that really seemed to be characterized by the patient's disease, that seemed to characterize the patient's disease progression. Then, in order to really dig deeper, working in collaboration with the domain expert, we specified anchors for those, and we iterated. And in this way, we discovered the full set of interesting variables that we wanted to model. Yep.
Did you measure how good an anchor these were? Like, are some comorbidities better anchors than others?
Great. You'll see. I think we'll answer that question in just a few minutes when I show you what the graph looks like that's learned. Yep.
Were all the other weights in that X to O network 0? They weren't part of an anchor.
They're
So it's like a pretty sparse.
They're explicitly non-zero, actually. It's opposite. So for an anchor, we say that it only has a single parent. Everything that's not an anchor can have arbitrarily many parents. Is that clear? Okay. Yep.
And so the anchors that you had in that later table, you iterated yourself on that, or did a doctor say that these are the ones that are especially trustworthy?
We started out with just a subset of these we wanted to model things that we wanted to understand what happens along disease progression according to these axes, but just a subset of them originally. And then we included a few additional hidden variables that didn't have any anchors associated to them. And after doing unsupervised learning in just a preliminary development stage, they discovered some topics where we realized, oh shoot, we should have included those in there. And then we added them in with corresponding anchors. And so you can think about this as an exploratory data analysis pipeline. Yep.
Is there a chance that these aren't anchors?
Yes. So there's definitely the chance that these may not be anchors. It's related to the question that was asked a second ago. So for example, there might be some chance that the morbid obesity diagnosis code might be coded for a patient more often for a patient who has, let's say, asthma. This is a bad example. And in which case that would correspond to there truly existing an edge from asthma to this anchor, which would be a violation of the anchor assumption. All right, so we chose these to make that unlikely, but it could happen. And it's not easily testable. So this is another example of an untestable assumption, just like we saw lots of other examples already in today's lecture and in the causal inference lectures. If we had some ground truth data, like if we had done chart review for some number of patients and we actually labeled these conditions, then we could test that anchor assumption. But here we're assuming that we don't actually know the ground truth of these conditions.
Is there a reason why you choose such high-level comorbidities? Like, I imagine you could go more specific. Even say in diabetes, you could try to subtype the diabetes based off of some other model and sort of use that as a single layer. But it seems to, at least this model seems to choose something that's relatively high level. I'm just curious the reason.
Yeah, so that was a design choice that we made. There are many, many directions for follow-up work, one of which would be to use a hierarchical model here. But we hadn't gone that direction. Another obvious direction for follow-up work would be to do simultaneous subtyping with this staging by introducing another random variable, which is, let's say, the disease subtype, and making everything a function of that. OK, so I've talked about the vertical slice, and I've talked about the topmost slice. But what I still need to tell you about is how these phenotypes relate to the observed disease stage. So for this, we use I don't remember the exact technical terminology. Factored Markov model. Is that right, Pete? Factorized Markov model. I mean, this is a term that exists in the graphical models literature, but I don't remember right now. So what we're saying is that each of these Markov chains, so each of these So each of these x1 up to xt, so this we'll say is the first one. I'll call it diabetes. This is the second one, which I'll say is depression. We're going to assume that each one of these Markov chains is conditionally independent of each other given the disease stage. So it's the disease stage which ties everything together. So the graphical model looks like this. And so on, OK? So in particular, there are no edges between, let's say, the diabetes variable and the depression variable. All correlations between these conditions is assumed to be mediated by the disease stage variable. And that's a critical assumption that we had to make. Does anyone know why? What would go wrong if we didn't make that assumption? So for example, what would go wrong if we had something look like this? x1, what is my notation? x11, x12, x13, and suppose we had edges between them, a complete graph, and we had, let's say, also the s variable with edges to everything. What would happen in that case where we're not assuming that the x's are conditionally independent given s? So I want you to think about this in terms of distributions. So remember, we're going to learn how to do disease progression through learning the parameters of this model. And so if we set this up if we set up the learning problem in a way which is unidentifiable, then we're going to be screwed. We're not going to be able to learn anything about disease progression. So what would happen in this situation? Someone who hasn't spoken today, ideally. Do any of you remember from, let's say, perhaps an earlier machine learning class, what types of distributions a complete graph, a complete Bayesian network could represent? The answer is all distributions, because it corresponds to any factorization of the joint distribution. And so if you allowed these x variables to be fully connected to each other, so for example, saying that depression depends on diabetes in addition to stage, then in fact, you don't even need this stage variable in here. The marginal you can fit any distribution on these x variables even without the s variable at all. And so the model could learn to simply ignore the s variable, which would be exactly not our goal, because our goal is to learn something about the disease stage. And in fact, we're going to be wanting to make assumptions on the progression of disease stage, which is going to help us learn. So by assuming conditional independence between these x variables, it's going to force all of the correlations to have to be mediated by that s variable, and it's going to remove some of that unidentifiability that would otherwise exist. This is a subtle but very important point. So the way that we're going to parameterize the conditional distribution, so first of all, I'm going to assume these x's are all binary. So either the patient has diabetes or they don't have diabetes. I'm going to suppose that, and this is, again, another assumption we're making. I'm going to suppose that if once you already have a comorbidity, then you always have it. So for example, once this is 1, then all subsequent ones are also going to be 1. Hold the question for just a second. I'm also going to make an assumption that later stages of the disease are more likely to develop the comorbidity. So in particular, one can formalize that mathematically as probability of x, I'll just say xi being 1 given s, I'll say st equals little s, comma xt minus 1 equals 0, I'm going to suppose that this is larger than or equal to probability of xt equals 1 given st equals s prime and xt minus 1 equals 0 for all s prime less than s. Okay? So I'm saying as you get further along in the disease stage, you're more likely to observe one of these complications. And again, this is an assumption that we're putting into the learning algorithm, but we found that these types of assumptions are really critical in order to learn disease progression models when you don't have a large amount of data. And note that this is just a linear inequality on the parameters of the model. And so one can use a convex optimization algorithm during learning, during the maximum likelihood estimation step of this algorithm, where you just put a linear inequality into the convex optimization problem to enforce this constraint. There were a couple of questions.
Is there generally like a quick way to check whether a model is unidentifiable, or?
So there are ways to try to check to see if a model is unidentifiable. It's beyond the scope of the class, but I'll just briefly mention one of the techniques. So you could ask the identifiability question by looking at moments of the distribution. For example, you could talk about it as a function of all of the observed moments of the distribution that you get from the data. Now, the observed data here are not the s's and x's, but rather the o's. So you can look at the joint distribution on the o's. And then you can ask questions about, if I was to perturb, so suppose I was to choose a random set of parameters in the model, is there any way to do a perturbation of the parameters of the model which leave the observed marginal distribution on the o's identical? And often when you're in the setting of non-identifiability, you can sort of take the gradient of a function and see, and you can sort of find that there is some wiggle space, and then you show that, okay, they're actually, this objective function is actually unidentifiable. Now, that type of technique is widely used when studying what are known as method of moments algorithms, or estimation algorithms in learning latent variable models. But they would be much, much harder to apply in this type of setting because first of all, these are much more complex models, and estimating the corresponding moments is going to be very hard because they're very high dimensional. And second, because I'm actually conflating two different things when I talk about identifiability. One statement is sort of the infinite data identifiability, and the second question is your ability to actually learn a good model from a small amount of data, which is a sample complexity. And these constraints that I'm putting in, even if they don't affect the actual identifiability of the model, they could be extremely important for improving the sample complexity of the learning algorithm. Was there another question? So we evaluated this using a data set of almost 4,000 patients, where again, each patient we observed for only a couple of years, 1 to 3 years. And the observations that we observed were 264 diagnosis codes, the presence or absence of each of those diagnosis codes during any 3-month interval. Overall, there were almost 200,000 observations of diagnosis codes in this data set. The learning algorithm that we used was expectation maximization. Remember, there are a number of hidden variables here, and so if you want to maximize if you want to learn the parameters that maximize the likelihood of those observations O, then you have to marginalize over those hidden variables, and EM is one way to try to find a local optima of that likelihood function. With the key caveat that one has to do approximate inference during the E step here, because this model is not tractable. There's no closed form, for example, dynamic programming algorithm for doing posterior inference in this model, given its complexity. And so what we used was a Gibbs sampler to do approximate inference within that E step. And we used we did block sampling of the Markov chains, where we sort of combined a Gibbs sampler with a dynamic programming algorithm, which improved the mixing rate of the Markov chain, for those of you who are familiar with those concepts. And in the M step of the learning algorithm, when one has to learn the parameters of the distribution, the only complex part of this model is the continuous time Markov process. And there's actually been previous literature from the physics community which shows how you can really, which gives you analytic closed-form solutions for that M step of that continuous time Markov process. Now, if I were to do this again today, I would have done it a little bit differently. I would still think about modeling this problem in a very similar way, but I would do learning using a variational lower bound of the likelihood with a recognition network in order to very quickly get you a lower bound of the likelihood. And for those of you who are familiar with variational autoencoders, that's precisely the idea that is used there for learning variational autoencoders. So that's the way I would approach this if I was to do it again. There's just one or two other extensions I want to mention. The first one is something which one more customization we made for COPD, which is that we enforced monotonic stage progression. So we said that, so here I talked about a type of monotonicity in terms of the conditional distribution of x given s, but one could also put an assumption in the, I already talked about that, but one could also put an assumption on P of s, s of t given s of t minus 1, which is implicitly an assumption on q. And I gave you a hint of how one might do that over here when I said that you might put zeros to the left-hand side, meaning you can never go to the left. And indeed we did something like that here as well, which is another type of constraint. And finally, we regularized the learning problem by asking that graph involving the conditions, the comorbidities, and the diagnosis codes be sparse by putting a beta prior on those edge weights. So here's what one learned. So the first thing I'm going to do is I'm going to show you the, we talked about how we specified anchors, but I told you that the anchors weren't the whole story, that we were able to infer much more interesting things about the hidden variables given all of the observations we have. So here I'm showing you several of the phenotypes that were learned by this unsupervised learning algorithm. First, the phenotype for kidney disease. In red here, I'm showing you the anchor variables that we chose for kidney disease. And what you'll notice are a couple of things. First, the weight, which you should think about as being proportional in some way to how often you would see that diagnosis code given that the patient had kidney disease. The weights are all far less than 1. Right? So there is some noise in this process of when you observe a diagnosis code for a patient. The second thing you observe is that there are a number of other diagnosis codes that are observed to be which are explained by this kidney disease comorbidity, such as anemia, urinary tract infections, and so on. And that aligns well with what's known in the medical literature about kidney disease. You could look at another example for lung cancer. In red here, I'm showing you the anchors that we had pre-specified for these, which mean that these diagnosis codes could only be explained by the lung cancer comorbidity. And these are the noise rates that are learned for them. And that's everything else. And here's one more example of lung infection where there was only a single anchor that we specified for pneumonia. And you see all of the other things that are automatically associated to that as by the unsupervised learning algorithm. Yep?
So how do you compute the weight? You don't know the ground truth for the mobility, right?
Right. So that's what the unsupervised learning algorithm is doing. So these weights are learned. And I'm showing you something like a point estimate of the parameters that are learned by the learning algorithm.
And so it's not
just like if you learn a hidden Markov model, you learn some transition emission distribution. Same thing here. Right, so, and this should look a lot like what you would see when you do topic modeling on a text corpora, right? You would discover a topic. This is analogous to a topic. It's a discrete topic, meaning it either occurs or doesn't occur for a patient. And you would discover some word topic distribution. This is analogous to that word topic distribution for a topic in a topic model. So one could then use the model to answer a couple of the original questions we set out to solve. The first one is, given a patient's data, which I'm illustrating here on the bottom, I have artificially separated it out into 3 different comorbidities, and a star denotes an observation of a data type of that one. But this was artificially done by us, and it was not given to the learning algorithm. One can infer when a patient started with each one of these comorbidities, and also so for the full 3-year time range that we have data for the patient, what stage was the patient in the disease at any one point in time. So this model infers that the patient starts out in stage 1, and about half a year through the data collection process transitions into stage 2 of COPD. Another thing that one could do using this model is to simulate from the model and answer the question of what would, let's say, a 20-year trajectory of the disease look like. Here I'm showing you a 10-year trajectory. And again, only 1 to 3 years of data was used for any one patient during learning. So this is the first time where you see those axes, those comorbidities, really start to show up as being important as the way of reading out from the model. Here we've thrown away those O's, those diagnosis codes altogether, and we only care about what we conjecture is truly happening to the patient, those X variables, which are unobserved during training. So what we conjecture is that kidney disease is very uncommon in stage 1 of the disease and increases slowly as you transition from stage 2 to stage 3 to stage 4 of the disease, and then really bumps up towards stage 5 and stage 6 of the disease. So you should read this as saying that in stage 6 of the disease, over 60% of people have kidney disease. Now, the time intervals here, so how I've chosen these, where to put these triangles, I've chosen them based on the average amount of time it takes to transition from one stage to the next stage, according to the learned parameters of the model. So you can see that sort of stages 1, 2, and 3, and 4 sort of take a long period of amount of time to transition between those 4 stages, and then there's a very small amount of time between transitioning from stage 5 to stage 6 on average. So that's for kidney disease. One could also read this out for other of the comorbidities. So in orange here, in yellow here is diabetes, in black here is musculoskeletal conditions, and in red here is cardiovascular disease. And so one of the interesting inferences made by this learning algorithm is that even in stage 1 of COPD, very early in the trajectory, we are seeing patients with large amounts of cardiovascular disease. Again, this is something that one could look at the medical literature to see does it align with what we expect, and it does. So even in patients with mild to moderate COPD, the leading cause of morbidity is cardiovascular disease. Again, this is just a sanity check that what this model is learning for a common disease actually aligns with medical knowledge. So that's all I wanted to say about this probabilistic model approach to disease progression modeling from cross-sectional data. I want you to hold your questions so that I can get through the rest of the material, and you could ask me after class. So next I want to talk about these pseudo-time methods, which are a very different approach for trying to align patients into early to late disease stage. These approaches were really popularized in the last 5 years due to the explosion in single-cell sequencing experiments in the biology community. Single-cell sequencing is a way to really understand not just what is the average gene expression, but on a cell-by-cell basis, can we understand what is expressed in each cell? So at a very high level, the way this works is you take a solid tissue, you do a number of procedures in order to isolate out individual cells from that tissue. Then you're going to extract the RNA from those individual cells. You go through another complex procedure which somehow barcodes each of the RNA from each individual cell, mixes them all together, does sequencing of it, and then deconvolves it so that you can see what was the original RNA expression for each of the individual cells. Now, the goal of these pseudo-time algorithms is to take that type of data and then to attempt to align cells to some trajectory. So if you look at the very top of this figure, figure A, that's the picture that you should have in your mind. In the real world, cells are evolving with time. For example, B cells will have a well-characterized evolution between different cellular states. And what we'd like to be able to understand, given that you have cross-sectional data, so you can imagine you have a whole collection of cells, each one in a different stage of differentiation. Could you somehow order them into where they were in different stages of differentiation? So that's the goal. We want to take this. So there exists some true ordering that I'm showing from dark to light. The capture process is going to ignore what the ordering information was, because all we're doing is getting a collection of cells that are in different stages. And then we're going to use this pseudo-time method to try to resort them so that you could figure out, oh, these were the cells in the early stage and these were the cells in the late stage. And of course, there's an analogy here to the pictures I showed you in the earlier part of the lecture. Once you have this alignment of cells into stages, then you could answer some really interesting scientific questions. For example, you could ask of a variety of different genes, which genes are expressed at which points in time. So you might see that gene A is very highly expressed and very early in this cell's differentiation, and is not expressed very much towards the end. And that might give you new biological insights. So these methods could immediately be applied, I believe, to disease progression modeling, where I want you to think about each cell as now a patient, and that patient has a number of observations. For this data, the observations are RNA expression for that cell, but in our data, the observations might be symptoms that we observe for the patient, for example. And then the goal is, given those cross-sectional observations, to sort them. And once you have that sorting, then you could answer scientific questions, such as I mentioned, of a number of different genes, which genes are expressed when. So here I'm showing you sort of the density of when this particular gene is expressed as a function of pseudo-time. Analogously, for disease progression modeling, you should think of that as being a symptom. So you could ask, OK, suppose there is some true progression of the disease. When do patients typically develop diabetes or cardiovascular symptoms? And so for cardiovascular, going back to the COPD example, you might imagine that there's a peak very early in the disease stage. For diabetes, it might be in a later disease stage. Right? So is the analogy clear? So this community, which has been developing methods for studying single-cell gene expression data, has just exploded in the last 10 years. So I lost count of how many different methods there are, but if I had a guess, I'd say 50 to 200 different methods for this problem. There was a paper, which is one of the optional readings for today's lecture, that just came out earlier this month, which looks at a comparison of these different trajectory inference methods. And this picture gives a really interesting illustration of what are some of the assumptions made by these algorithms. So for example, the first question when you try to figure out which method of these tons of methods to use is, do you expect multiple disconnected trajectories? What might be a reason why you would expect multiple disconnected trajectories for disease progression modeling? TAs should not answer. Different subtypes would be an example. So suppose the answer is no, as we've been assuming for most of this lecture. then you might ask, OK, there might only be a single trajectory, because we're only assuming there's a single disease subtype. But do we expect a particular topology? Now, everything that we've been talking about up until now has been a linear topology, meaning there's a linear projection. There's such notion of early and late to stage. But in fact, the linear trajectory may not be realistic. Maybe the trajectory looks a little bit more like this bifurcation. Right? Maybe patients look the same very early in the disease stage, but then suddenly something might happen which causes some patients to go this way and some patients to go that way. Any idea what that might be in a clinical setting? Treatment. That's great. Right? So maybe these patients got t equals 0, and maybe these patients got t equals 1. And maybe for whatever reason, we don't even have good data on what treatments patients got, so we don't actually observe the treatment. Right? Then you might want to be able to discover that bifurcation directly from the data. Then that might suggest going back to the original source of the data to ask what differentiated these patients at this point in time. And you might discover, oh, there was something in the data that we didn't record, such as treatment. Right? So there are a variety of methods to try to infer these pseudo-times under a variety of different assumptions. What I'll do in the next few minutes is just give you an inkling of how 2 of the methods work. And I chose these to be representative examples. The first example is an approach based on building a minimum spanning tree. And this algorithm I'm going to describe goes by the name of Monocle. It was published in 2014 in this paper by Trapnell et al. But it builds very heavily on an earlier published paper from 2003 that I'm also citing here. So the way that this algorithm works is as follows. It starts with, as we've been assuming all along, cross-sectional data, which lives in some high-dimensional space. I'm drawing that in the top left here. Each data point corresponds to some patient or some cell. The first step of the algorithm is to do dimensionality reduction. And there are many ways to do dimensionality reduction. You could do principal components analysis, or for example, you could do independent components analysis. This paper uses independent components analysis. What ICA is going to do is going to attempt to find a number of different components that seem to be as independent from one another as possible. Then you're going to represent the data now in this lower dimensional space. And in many of these papers, it's quite astonishing to me, they actually use dimension 2. So they'll go all the way down a 2-dimensional space where you can actually plot all of the data. It's not at all obvious to me why you would want to do that. And for clinical data, I think that might be a very poor choice. Then what they do is they build a minimum spanning tree on all of the patients or cells. So the way that one does that is you create a graph by drawing an edge between every pair of nodes, where the weight of the edge is the Euclidean distance between those 2 points. And then, so for example, there is this edge from here to here, there's an edge from here to here, and so on. And then given that weighted graph, we're going to find the minimum spanning tree of that graph. And what I'm showing you here is the minimum spanning tree of the corresponding graph. Okay? Next, what one will do is you'll look for the longest path in that tree. Remember, finding the longest path in a graph, in an arbitrary graph, has a name. It's called the traveling salesman problem, and it's an NP-hard problem. How has that gotten around here? Well, this is not an arbitrary graph. This is actually a tree. So here's a poor algorithm. Here's a bad algorithm for finding the longest path. No, I won't talk about that. So one finds the longest path in a tree, in the tree, and then what one does is one says, OK, one side of the path corresponds to, let's say, early disease stage, and the other side of the path corresponds to late disease stage. And it allows for the fact that there might be some bifurcations. So for example, you see here that there is a bifurcation over here. And as we discussed earlier, you have to have some way of differentiating what the beginning is and what the end should be. And that's where some side information might become useful. So here's an illustration of applying that method to some real data. So every point here is a cell after doing dimensionality reduction. The edges between those points correspond to the edges of the minimum spanning tree. And now what the authors have done is they've actually used some side information that they had in order to color each of the nodes based on what part of the cell differentiation process that cell is believed to be in. And what one discovers is that in fact this is very sensible, that all of these points are in a much earlier disease stage, the analogous thing of that, than these points, and this is a sensible bifurcation. Next, I want to talk about a slightly different approach to. So this is the whole story, by the way, right? It's a conceptually very, very simple approach. Next, I want to talk about a different approach, which now tries to return back to the probabilistic approaches that we had earlier in the lecture. This new approach is going to be based on Gaussian processes. So Gaussian processes have come up a couple of times in lecture, but I've never actually formally defined them for you. So in order for what I'm going to say next to make sense, I'm going to formally define for you what a Gaussian process is. A Gaussian process, mu, for a collection of time points, t1 through t capital N, is defined by a joint distribution, mu of those time points, which is a Gaussian distribution. So we're going to say that the function value for these t different time points is just a Gaussian, which for the purpose of today's lecture, I'm going to assume is zero mean, and where the covariance function is given to you by this capital K. It's a covariance function of the time points, of the input points. And so if you look, this has to be a matrix of dimension capital N by capital N. And if you look at the I1 and I2th entry, if you look at any entry of that matrix, we're defining it to be given to you by the following kernel function. It looks at the exponential of the negative Euclidean distance squared between those two time points. Intuitively, what this is saying is that if you have two time points that are very close to one another, then this kernel function is going to be very large. If you have two time points that are very far from one another, then this is very large. It's a very large negative number, and so this is going to be very small. So the kernel function for two inputs that are very far from one another are very small. The kernel function for inputs that are very close to each other is large, and thus what we're saying here is that there's going to be some correlation between nearby data points. And that's the way which we're going to specify a distribution of functions. If one were to sample from this Gaussian with the covariance function specified in the way I did, what one gets out is something that looks like this. So this I'm assuming here that these curves look really dense, and that's because I'm assuming that n is extremely large here. If n was small, let's say 3, there'd only be 3 time points here. Okay, and so if you can make this distribution of functions be arbitrarily complex by playing with this little l. So for example, if you made little l be very small, then what you get are these really spiky functions that I'm showing you in a very light color. If you make little l be very large, you get these very smooth functions. Right? So this is a way to get a function. This is a way to get a distribution over functions just by sampling from this Gaussian process. What this paper does from Campbell and Yao and published 2 years ago in PLOS Computational Biology is they assume that the observations that you have are drawn from a Gaussian distribution whose mean is given to you by the Gaussian process. So if you think back to the story that we drew earlier, suppose that the data lived in just one dimension. And suppose we actually knew the sorting of patients. So we actually knew which patients are very early in time, which patients are very late in time. You might imagine that single biomarker A, you might imagine that the function which tells you what the biomarker's value is as a function of time might be something like this, right? Or maybe it's something like that, okay? So it might be a function that's increasing or a function that's decreasing. And this function is precisely what this mu, this Gaussian process, is meant to model. The only difference is that now one can model the Gaussian process instead of just being a single dimension. One can imagine having several different dimensions. So this p denotes the number of dimensions, right, which corresponds to, in some sense, to the number of synthetic biomarkers that you might conjecture exist. Now here we truly don't know the sorting of patients into early versus late stage. And so the time points t are themselves assumed to be latent variables that are drawn from a truncated normal distribution that looks like this. So you might make some assumption that the time intervals for when a patient comes in might be, maybe patients come in really typically very in the middle of the disease stage, or maybe you assume this is something flat, and so patients come in sort of throughout the disease stage. But the time point itself is latent. So now the generative process for the data is as follows. You first sample a time point from this truncated normal distribution. Then you look to see and you sample from the very beginning, you sample this curve, mu. And then you look to see what is the value of mu for the sampled time point. And that gives you the expected value you should expect to see for that patient. And the one then jointly optimizes this to try to find the curve mu, which has highest posterior probability, and that is how you read out from the model both what the latent progression looks like, and if you look at the posterior distribution over the t's that are inferred for each individual, you get the inferred location along the trajectory for each individual. And I'll stop there. I'll post the slides online for this last piece, but I'll let you read the paper on your own.